Hello and welcome to the fourth video of the M2 chapter Impulses and Collisions. Quick question on the screen to review our previous work. A smooth sphere falls from rest onto a smooth horizontal plane. It takes 2 seconds to reach the plane. So it's falling from rest. It takes 2 seconds to reach the plane. The coefficient of restitution between the sphere and the plane is 0.64. Find the time it takes after rebound for the sphere to reach the plane a second time. So it's starting here from rest, it's going to drop, gaining speed. Just before it hits, I need to know the speed of that. Then I can use the coefficient of restitution to find the speed immediately after it hits. It will rebound, and from that point I need to know how long will it take to bounce up here, and then to fall back down to the plane again for a second bounce. So before anything else, I'm going to calculate what speed it is hitting the plane here. To do that, I need constant acceleration. U is 0, t is 2, a is equal to 9.8 if I take downwards to be positive. V is my question mark. So V is equal to u plus at, 0 plus 9.8. Or actually, given that I'm going to use this number in a following calculation later, I might keep it as g. G times 2. So V is equal to 2g, where I'll use 9.8 as and when I want a final answer. After that impact, the sphere is going to be then moving upwards, and I need to know from this point how long does it take for it to go up, come to instantaneous rest, fall back down again, and hit the plane for a second time. To know that, I need to first know what is the speed here, and it is not the same as this because we have a coefficient of restitution where it is not a perfectly elastic collision. So to find this speed here, I'm going to need the ratio for E, where the speed of separation, which is u in blue, divided by the speed of approach, which is the v in red. This is E, and this has to equal 0.64. And we know v in red is 2g, so u in blue is equal to 2g times 0.64, which is 1.28 g meters per second for u, the initial speed immediately after the impact where the ball is starting to come back up. So that's 1.28 g. And now I have another constant acceleration question. So let's take upwards to be positive now. Then I have u is equal to 1.28 g. A is equal to negative g. Change this over here to g, just because it was annoying me. T is the thing that we want, and we also know the displacement because we want the time when the ball starts to come back up to the time where it hits the surface again for a second time, so the displacement here from where it is now will be 0. So here we're using s is equal to ut plus a half at squared, where s is 0, 1.28 g times t, plus a half times minus g, so minus g over 2 t squared. If I multiply everything by 2, that gives me 0 equals 2.56 gt minus gt squared. Then we can factorize out the g and the t. Gt is 2.56 minus t, and the gt outside the brackets gives us the result t is equal to 0, which is where it is now, and the result within the bracket gives us t is equal to 2.56 seconds, which is the time it takes to come back to the plane and hit for a second time. This here then is our final answer to the question. In this video, we're going to solve problems involving a change in energy due to a collision. So we know that when two particles collide, linear momentum is conserved. However, the total kinetic energy of the system is not conserved, not unless the collision happens to be perfectly elastic, in which case it is. During the collision, the kinetic energy that we're losing is being transformed into other types of energy. For example, sound. If two things hit each other, they often produce a sound. There might be a little bit of heat energy as well. But although the collision will cause the system as a whole to lose some kinetic energy, unless we do have a perfectly elastic collision, the individual particles might lose or gain kinetic energy. So as you focus on an individual particle, you might see a gain in kinetic energy or you might see a loss in kinetic energy, but the system as a whole will lose some kinetic energy. Now I've put here specifically a collision will cause a loss of kinetic energy. We will see in one of our examples in this video something that's not a collision and there will be a gain in kinetic energy. So you still need to be careful of the context of your question. Just in case you, like me, think that this is a little bit strange, that you can lose kinetic energy but not lose linear momentum, I've got a quick example just to show that it can happen. Here we have, before impact, 10 meters per second mass m, 0 meters per second mass m. So the linear momentum is 10m plus 0 before impact, 2m plus 8m after impact, and you can see very easily that this is the same as this linear momentum is conserved. However, if we look at the total kinetic energy before the impact, we've got a half times m times v squared for the first particle, and a half times m times v squared for the second particle, gives us a total of 50m, and after the impact, the total kinetic energy of the system is a half times m times v squared, plus a half times m times v squared, which gives us 2m plus 32m, a total of only 34m joules of energy. So you can see that the kinetic energy has decreased even though linear momentum has stayed the same. And this is because linear momentum is mass times velocity, whereas kinetic energy is a half mass times velocity squared. The squareds here, of course, making the difference. So here's our first example. Two spheres A and B have masses 3 and 5 respectively. A and B move towards each other in opposite directions along the same straight line on a smooth horizontal surface with speeds 3 and 2. That's a lot of words for a very simple setup. Here we've got 3 kilograms for A, 5 kilograms for B, 3 this way, 2 this way on the speeds. Given the coefficient of restitution is 3/5, find the velocity of the spheres after the collision. Okay, this is no different to what we have done in previous videos. So we've got v1 here, v2 here. I will take this direction as my positive direction. So we're going to use conservation of linear momentum to help us solve part A. On the left, we've got 3 times 3, plus 5 times minus 2. On the right, 3 times v1, plus 5 times v2. 9 minus 10 is minus 1. 3v1 plus 5v2. And then we have Newton's law of restitution. This is conservation of linear momentum. Newton's law of restitution. We know that v2 minus v1 divided by the speed of approach, 3 minus minus 2, or 3 plus 2 is 5, must equal E, which is 3/5. And if I rearrange this, we get v2 is equal to 3 plus v1, which I can substitute in here. So combining those two together, we get minus 1 is equal to 3v1 plus 5 lots of 3 plus v1, which gives minus 16 on the left, 8v1, so v1 is equal to minus 2. Putting that back into here gives v2 equal to 1. So we can see that both have lost speed and both have changed direction. v1 is negative, so the particle is moving in this direction. v2 is positive, so it's moving in this direction. Part B, find the loss of kinetic energy due to the impact. So we're going to do exactly what we did just on the previous screen. I'm going to find the total kinetic energy before the impact, total kinetic energy after the impact, and just find the difference between them. Before the impact, the kinetic energy is a half times 3 squared for particle A, plus a half times the mass 5 times the speed squared for particle B, which gives me a total of 47/2. Over here, after the impact, if I can squeeze it in here somewhere in white, the kinetic energy is a half times the mass times the speed of particle A squared, and v1 is minus 2, so that speed is 2 squared, plus a half times the mass of particle B times its speed squared, and that gives me a total of 17 over 2. Finally, squeezed right in the corner here, the loss of kinetic energy due to the collision is equal to 47 over 2 minus 17 over 2, which is 15 joules of energy lost due to the collision. Looking at the screen now, it looks kind of messy and all over the place, but I hope you've followed what I've done. Example 2. A baseball pitching machine of mass 60 kilograms fires a baseball of mass 0.15 kilograms horizontally with speed 30 meters a second. This is the example that is not a collision. So initially, they're not moving. The baseball machine and the baseball are both stationary. So if I do the machine as a box and the baseball as a ball ready to be ejected, this is 60, the ball is 0.15, and they both have speed 0 meters per second. Then the machine fires the ball. So we have the machine here, 60 kilograms still. The ball is now traveling this way, still 0.15 kilograms, but with a speed of 30 meters a second. And part A is asking us to find the velocity of the machine after the baseball has been pitched. So if I take my usual approach and call this V with the positive direction here, even though I know for sure for linear momentum to be conserved, it must be traveling this direction. We've got 0 linear momentum, and afterwards 60V plus 0.15 times 30. Rearrange, we find that the velocity of the machine is 0.075 meters per second. And if you saw this happening, you might call that the kickback of the machine. Part B, find the total kinetic energy generated on pitching. This is one situation where we're going to gain kinetic energy because initially there's no kinetic energy. And then the ball is moving and the machine is moving, so there's kinetic energy generated. So that was part A. Part B, the kinetic energy after pitching is a half times the mass of the machine times its speed squared, plus a half times the mass of the ball times its speed squared, which gives us 10827 over 160 joules of energy. That's the kinetic energy after pitching. It's also the gain in kinetic energy because initially there was none. Part C, show that the ratio of the energy of the machine to the energy of the baseball is equal to the ratio of the speed of the machine to the speed of the baseball. Okay, we have most of the information. This is the kinetic energy of the machine, kinetic energy of the baseball. So half times 60 times 0.075 squared to the energy of the baseball, half times 0.15 times 30 squared. I'm rewriting that because from the question I know both ratios are going to be the same, and I want to be clear which one has come from where. The left hand side here gives me 27 over 160. The right hand side 135 over 2. Simplifying that as far as possible, we get to 1 to 400. Now the ratio of the speed of the machine to the speed of the baseball is 0.075 to 30, and dividing both sides by 0.075 gives us the same ratio, 1 to 400. So they are indeed the same. Next example. Two particles A and B of masses 200 and 300 grams respectively. Be careful, 200 grams, change that into kilograms straight away. We've got 0.2 kilograms, 0.3 kilograms. They are connected by a light inextensible string. The particles are side by side at rest on a smooth floor. And A is projected with speed 6 meters a second directly away from B. So let's say we've got A here, B here. This is 0.2, 0.3. Initially they are both at rest, but then A is projected with a speed 6 meters per second away from B. When the string becomes taut, so it's now taut or tight, particle B, of course, is pulled into motion with A, and A and B together move with a common speed in the direction of the projection of A. So they're going this way, they're moving together, and they have one common speed because they're connected by a taut, inextensible string. This is 0.2, this is 0.3, but effectively they now have a combined system mass of 0.5 kilograms. This is similar to two particles coalescing on impact. They're separate initially, and then here they're moving together. We can consider them a single particle. Part A, find the common speed of the particles after the string becomes taut. So using conservation of linear momentum, we have 6 times 0.2 plus 0.3 times 0 must equal the combined mass times the common speed v. So v must equal 2.4 meters per second. Part A. Find the loss of total kinetic energy due to the pull. Part B. Kinetic energy before the pull is 1/2 times mass of particle A times the square of the speed of particle A, plus for particle B that's 0 because it's got 0 speed. 3.6 joules of energy. Kinetic energy after the pull, we've got 1/2 times the combined mass times the common speed squared, which gives us 1.44 joules of energy. So finally, the loss of kinetic energy is equal to 3.6 minus 1.44, which is 2.16 joules of energy lost due to the pull. Fourth and final example. A particle of mass 0.1 kilograms is moving with velocity this. When it receives an impulse of this, find the change in kinetic energy of the particle due to the impulse. So we're using I is equal to mv minus mu, where these are vectors. Putting in the vectors, we get minus 1, 3 is equal to 0.1 times v minus 0.1 times u, 2, 5. So v is equal to 10 lots of this plus this, which is minus 8 and 35. I've gone right into that without really explaining why I've done that. We need to find the change in kinetic energy, and for kinetic energy we need to know the speed of the particle before and after the impulse. For the speed before the impulse, we already know how to calculate that from here, but to calculate the speed after the impulse we needed to find the velocity after the impulse. Now I need to calculate the speed so I can find the kinetic energy. Before the impulse, we've got 2, 5. So the magnitude of this, 2 squared plus 5 squared, square rooted, is equal to the square root of 29. The kinetic energy then is 1/2 times the mass times the speed squared, so that's square root of 29 squared, 29, which is 1.45 joules of energy. After the impulse, the velocity is minus 8.35. The speed is the magnitude of that, square root of 8 or minus 8 squared plus 35 squared, which is the square root of 1289. Kinetic energy is 1/2 times the mass times that squared, which brings it back to 1289, which is 64.45 joules of energy. Therefore the change in kinetic energy is 64.45 minus 1.45 is 63 joules of energy. I hope that's enough for you to have a go at some of these questions in exercise 5D. Maybe I'll see you for the final video in this chapter, successive impacts.